Every single time you click a link, stream a show, or send a message, your data starts this wild journey. But before we can even think about crossing oceans and continents, it has to take its very first step. And that step, it happens on something called the link layer, this invisible but totally essential connection that basically gets your data out the front door. So come on, let's peel back that layer and see what's really going on. We almost never think about this, right? You're on your laptop, your Wi-Fi router's sitting over there across the room. It all just works. But that little bit of empty space is a surprisingly complex and busy place. So what is actually happening in that gap? How does your data make that tiny, but absolutely critical, jump? Well, the hero of this little story is the link layer. It's the part of the whole network setup that has one very specific, very important job. It manages the journey of your data between two devices that are physically right next to each other. You can think of it as the local delivery service of the internet.
So here's the key thing to get. The link layer doesn't care about your data's final destination in, say, another country. Nope. Its only job is to get a packet of data from one node, like your computer, to the very next node in the chain, which is probably your router. It's all about making that single local hop successfully.
Okay, but before your data can even try to make that first jump, it has to be prepared. It can't just be sent out raw into the world. Just like if you were mailing something, it needs to be put into the right kind of container for its short trip. So to make this journey, the link layer takes your data, which at this point is called a datagram, and it wraps it up in a digital envelope. We call this envelope a frame. This whole wrapping process, it's called encapsulation, and it adds a header and a trailer to your data. It's kind of like putting the destination and return address on the envelope, all just for this one specific local hop. All right, so we've got our data in an envelope. But wait a minute. If you have a phone, a smart TV, and your laptop all connected to the same Wi-Fi, how does the frame know it's supposed to go to the router and not, your TV? It needs a very specific local address. And the answer to that question is the MAC address. MAC stands for Media Access Control, and it's a unique 48-bit serial number that is literally burned into every single network card ever made, whether it's in your phone for Wi-Fi, your computer for Ethernet, or in your headphones for Bluetooth. It is the device's physical fingerprint on the network. Every single MAC address is designed to be globally unique. Seriously, no two devices in the entire world should ever have the same one. And it doesn't change, no matter where you go. The best way to think about it, it's like a permanent, unlisted phone number for your hardware, and it's only used for making those local calls to other devices on the same network.
So, our data is now packaged up in a frame, and it's addressed with a MAC address. It's ready to be sent. But the physical world is a messy place. Whether that data is traveling over a copper wire or flying through the air as a radio wave, there's a real chance it could get damaged along the way.
Remember, the data we're sending is really just a series of electrical pulses or radio signals that represent ones and zeros. But things like random background noise or the signal just getting weaker over distance, that's called attenuation, can cause those bits to flip. A 1 might get misread as a 0 or a 0 as a 1. And if that happens, the data is completely corrupted, useless. So how do we deal with this? We use something called error detection. The device that's sending the data adds a few extra bits to the frame, called error detection and correction bits, or EDC. The best analogy is it's like putting a tamper-proof seal on an evidence bag. When the frame gets to its destination, the receiver checks the seal. If the seal is intact, the data is good to go. If it looks broken, it knows the data was corrupted, and it just throws the whole frame away. Now, there are a few ways to create this seal. Early methods like parity checking and checksums were pretty simple, but they could sometimes miss certain kinds of errors. That's exactly why modern networks like Ethernet and Wi-Fi rely on the real powerhouse, the cyclic redundancy check, or CRC. It runs a much more complex math problem to create a really robust digital fingerprint that is exceptionally good at sniffing out any corruption. Okay, so our frame is packaged, it's addressed, and now it's even insured against damage. It is ready to go. But now it faces its biggest challenge yet. How does it navigate a shared network where everyone is trying to talk at once? This is a huge problem, especially on Wi-Fi. Think about it. Your Wi-Fi network is a broadcast medium. It's like a single-lane road that every single device in your house has to share. If your phone and your laptop both try to send data at the exact same microsecond, their signals smash into each other, and the result is a collision. The data from both devices just turns into scrambled, useless noise. So to prevent total chaos, we need rules of the road. We call these multiple access protocols. And broadly speaking, there are three main strategies. First is channel partitioning, which is like dividing the road into separate lanes, giving everyone their own reserved time slot to talk. Then there's taking turns, which is like passing around a talking stick. You can only speak if you're holding the special token. And finally, there's random access, which is a lot like a polite cocktail party. You try to speak, but if you accidentally interrupt someone, you both say, oops, sorry, wait a random amount of time, and then try again. So let's zoom in on that cocktail party method, random access, because that's the one that Wi-Fi and classic Ethernet are built on. It's great because it lets a single device use the full speed of the network if no one else is talking. But it has to have a really good system for dealing with those inevitable collisions. And just to show you how hard this problem is, consider one of the very first random access protocols, called slotted aloha. Even in a perfect scenario, its absolute maximum efficiency was 37%. Just think about that for a second. That means nearly 2/3 of the network's potential was just wasted, either on dead silence or garbled collisions. We clearly needed a better way.
And this is where things get really clever. Modern systems use a protocol called CSMA, or Carrier Sense Multiple Access. And the core idea behind it is so simple and intuitive. Listen before you speak. Before a device even tries to send anything, it first listens to the channel to check if anyone else is talking. If it's clear, it sends. If it's busy, it waits. It's such a simple rule, but it dramatically reduces the number of collisions. So let's take a step back and pull all these pieces together and see why this first tiny local step is so incredibly important for, well, the entire internet. So here it is, the complete local journey in 5 steps. First, your data gets packaged into a frame. Second, it gets addressed with the destination MAC address of the very next hop, like your router. Third, it's ensured against corruption with those CRC error-checking bits. Fourth, it's sent out onto that shared road, carefully following the rules to avoid a collision. And finally, number 5, it arrives. It gets checked for errors, and if it's clean, the original data is unpacked and sent on its way. And here is the real kicker. Every email, every video, every single bit of data you send or receive has to go through this whole complicated local journey. Not just once, but over and over and over again, at every single hop from router to router across the entire planet. The link layer is what makes the global internet possible by perfectly managing one local hop at a time. Which, of course, leaves us with a pretty fascinating question for the future. As our homes fill up with smart fridges and smart lights and a dozen other gadgets all trying to share the same Wi-Fi road, are these polite listen before you speak rules going to be enough to handle all that traffic? Or are we heading towards a future of total digital gridlock right in our own living rooms?